First of all, I would like to express my gratitude to the organizers of this wonderful conference. This is a joint work with Professor Guglielmo Lanzani and Dr. Greta Chiaravalli from the Center for Nanoscience and Technology in Milano Politecnico. So the motivation of the research I'm going to present today is the cure of a very severe eye neuropathy, which is referred to as age-related macular degeneration, AMD. AMD basically is a progressive disease which leads upon time to a gradual loss of visual acuity and in extreme cases even to blindness. A huge number of people is affected worldwide by this disease, and in the order of 200 million people, approximately 11 million of them are located in the US. And more importantly, data show that US people over 75, 1/3 of these people, particularly males, are affected by this terrible disease. So the social gravity of this pathology requires for appropriate cure, appropriate therapeutical techniques. In the field of ophthalmology, typical approaches are based on topical drug administration and in extreme situations resorting to laser surgery, which of course is invasive and not necessarily resolving the disease. So over the last years, I would say over the last 10 years approximately, a lot of contributions have been made in the technology and the engineering technology in particular to propose alternative approaches. In particular, the group in the Italian Institute of Technology, which is conducted by Professor Fabio Benfenati, has developed very sophisticated techniques based on the subretinal injection of nanoparticles. Nanoparticles based on the use of conjugated polymers. The result of such administration is that, and this is shown by experiments, is that the animal model rats which are affected by retinitis pigmentosa have shown that the administration of drugs of these particles provides a persistent recuperation of the visual function. This is done through mediation by the nanoparticles of a light-evoked stimulation of retinal neurons. Now that is amazing, of course, but still the physical mechanisms which underlie the functioning of this nanoparticle approach remain still poorly understood. For these reasons, I have been trying over the last, I would say, 1.5 years to develop a mathematical model starting from the concepts up to reaching equations. This is because the system that we have talked about so far is very complicated, and particularly it is characterized, that is the most important feature in my opinion, by a strong heterogeneity, since we have the co-presence of neurons in aqueous environment and the prosthesis, which is in this case made by nanoparticles. Moreover, it is very difficult to replicate in vitro what happens actually in vivo conditions. That's the reason why in this presentation, to deal with this complicated problem, we devise a two-step approach to lead from a conceptual model up to reaching a mathematical model which can be used for quantitative predictions. As far as the conceptual model is concerned, You can see from this cartoon on the left a schematic picture of a little detail of the biohybrid system that we are dealing with. So as you can see, we have a neuron membrane, light which impinges on a little ball of approximately 100 nanometers radius. This is the nanoparticle. And then the nanoparticle is, as you see, immersed into a strongly heterogeneous medium, which is composed by an aqueous solution in, I would say, equilibrium conditions. And then on the opposite side, we have close to the neuronal membrane, a apparently porous medium, which represents in this model the interstitial cleft. And then we have a transition region, which we will call diffuse interface, which connects the extracellular side to the cleft region. Having introduced the structure of the problem, then the question is, in this conceptual approach, to figure out which are the most supposedly relevant mechanisms which determine the function of the device itself. We have identified a chain constituted by 6 processes. So light, as I said, impinges on the nanoparticle, and as a result, it converts into free charge carriers. These carriers, since they are charged, they move inside the bulk of the nanoparticle due to the superposition of drift and diffusion forces, and through their motion, they change their density because of particle-particle interaction. So they are not constant, uniformly distributed inside the nanoparticle. They have typically an asymmetric distribution, which in turn provides on the surface of the nanoparticle in touch with the aqueous solution several chemical oxidoreduction reactions, which in turn help determine the capacitive and conductive coupling between the nanoparticle, the aqueous solution, and finally the neuron, which in the end undergoes a depolarization, which is what experiments show. The complexity of the problem now appears clear, and in order to end up with a mathematically sound conclusion, which is numbers, in other words, we have to devise a system of equations, which I'm not going to tell you in all of the details because it would take too much time. Simply take into account the fact that we are now considering, for sake of simplicity, a one-dimensional geometrical representation of our three-dimensional model, the x-axis representing the principal direction of our investigation. On the left, we have the neuron. On the right, we have the extracellular medium, and in between, we have the nanoparticle and the transition region. On this part of the slide, we can see balance laws expressing balance of electrochemical quantities supplied by appropriate constitutive law, which express the drift diffusion and electrochemical electrodiffusion formalism under which charges and ions move in their respective domains. Of some interest are the boundary conditions at x equal to 0 and x on the right, because, for instance, we can see that the inner cytoplasm of the neuron is set to a fixed potential, V overline neuron. Such a potential is determined using equilibrium Goldman membrane potential equations. On the other side of the device, here on the right, far from the cleft, if you want, we assume equilibrium conditions for concentrations of ions and electric potential. So the problem, let me go back for a second to the geometrical picture, is to establish correct interface conditions across the interfaces separating the extracellular medium side from the cleft. Such interface conditions are critical in determining the overall performance of the model, mathematical model picture. As far as the nanoparticle domain, we assume for such a nanoparticle domain interface, transmission conditions for the normal component of the electric displacement and the normal component of the electric and hole current densities. All of these conditions allow to express mathematically the coupling between the nanoparticle and the surrounding environment. In the same locations, we have interface conditions as far as the motion of ions in the two aqueous subdomains, which are respectively the extracellular side and the cleft. Again, here we have a, I would say, a transmission condition which expresses mathematically the transit of ions across this delicate region, which is the diffuse interface, in which we assume that the ion permeability changes abruptly. All of these conditions are easily handleable in a finite element formulation in the traditional natural approach. So what is the scope of the model in the end of the day? Well, we want to use the model as a virtual laboratory. So we have seen beautiful presentations by previous speakers. All of them have been characterized by the ability of the speakers themselves to apply ideas into a laboratory context, a real laboratory context. And I do the same in my research. But as an applied mathematician, the idea is to use the model as a virtual lab, which is able to allow us to unravel the biophysical mechanisms on the one hand, and in particular to characterize the quantitative values of parameters which are very difficult, sometimes impossible to measure experimentally. Such parameters will be, I would say, taken in consideration during the simulation I'm going to show you. So the first simulation is without light. So in other words, there is no stimulation from outside, but the particle is there. And so if the particle is there, we can immediately see that the presence of the nanoparticle induces a modification of the original neuronal membrane potential. Assume that without nanoparticle, this black line, which represents the spatial distribution of the electric potential in the domain, would be flat and equal to 0. So that in homeostatic condition, in other words, the membrane potential would be exactly equal to minus 75 millivolt. So the presence of the nanoparticle is enough to induce a depolarization of 18 millivolt. So in other words, the presence of the nanoparticle still is going to trigger a neuronal activity. Of course, we are interested in switching light on, but before doing that, we want to investigate the effect of the permeability of ions in the diffuse interface region, which I told you a couple of minutes ago. Particularly, results show that if permeability of ions is increased, that of course increases the conductivity of the cleft, because we have more ions in the cleft, which means that the resistivity of the ion of the cleft consistently decreases. And what we see is that in the limit of infinitely high permeability, we go back to homeostatic conditions. So in other words, permeability, as expected, is shown by simulations to restore the homeostatic situations whenever it increases. Now we compare what happens for a given value of permeability when we switch light on compared to the light off simulation. And what we can see is the magenta curve that clearly indicates an extra depolarization of our of the neuron, and this is due to the presence of light. Finally, Another important parameter, which, as I told you, is very hard to access experimentally, is the lifetime of the superoxide O2 minus ions, which are catalyzed from the surface reactions that I told you about before, occurring at the interface between nanoparticle and the solution. So, parametrically speaking, these curves tell us that so these curves are parameterized by an increasing value of lifetime. If we assume that the lifetime is increasing, then we necessarily have a decrease of the molar density of superoxide in the cleft, because of course, if the superoxide lives more longly, then accordingly it reaches in a minor quantity the cleft. But this means that the resistivity of the cleft increases, and as a result, such an increase in resistivity gives rise to an extra depolarization in the order of 20 millivolts with respect to the previous conditions. So we have seen that these several mechanisms contribute in a different quantitative manner to enhance neuron depolarization. The conclusion of our analysis is that we have developed a theoretical model to describe these photoactivation of a neuron induced by injection subretinally of a nanoparticle made of a conjugated polymer. Simulations suggest that the main significant property which induces such interaction between neuron and nanoparticle is the high resistivity of the cleft region. So whenever we assume a decrease of ion permeability in the diffuse interface region, that of course contributes to enhance and promote more and more such a coupling, which is still even more enhanced by an increase of superoxide lifetime. And so I think that I tried to give you an idea of the complexity of the problem, how we dealt with conceptually, and how we translated such conceptual model into continuum-based equations, which provided us a quantitative indication of the relative weight of several concurring phenomena which determine the performance of the nanoparticle and are usually very hard to measure experimentally. This proves mathematical modeling as a valuable tool for a virtual laboratory analysis, which does not replace the experimental work, of course, but helps improve the comprehension of complicated systems like this. Thank you for your attention.